with some very interesting mathematical derivations. So first we will discuss. So I will be writing, explaining, and just let me know if you face any difficulty in understanding any of the step. You can interrupt me.
Okay,
I will be
sir.
a bit fast. Yeah, we have to cover this. Time dependent Schrodinger wave equation. So basically, it is a very important equation. Just like for classical mechanics, we have Newton's laws of motion, like the equation, second law of motion, F is equal to ma.
Yes, sir.
With that, we can like it describes the entire motion. Like we can get the trajectory of the particle at any time, and we can clearly identify the state of the particle at any time instant. Similarly, in quantum mechanics, this wave equation acts like that Schrodinger wave equation.
Okay, sir.
So, how it got originated? So, there is a very interesting story behind that, behind this wave equation. Like, what inspired Schrodinger? He's a very popular physicist. He got Nobel Prize for this equation. So, what inspired Schrodinger to basically discover this equation? So the idea is that at that time, de Broglie was very famous. And de Broglie hypothesis, you know that
Yes, sir.
dual nature of matter. So according to de Broglie, a moving particle a moving particle exhibits wave nature. A moving particle is always associated with a wave. So according to de Broglie, a moving particle is always associated with a wave. Now, at that time, this principle was very famous, very popular, and Schrodinger was highly inspired by this principle. Now, there was a curiosity among the scientists that, okay, we admit that moving particles, they exhibit wave. So, Schrodinger used to say that moving electrons will definitely exhibit a wave nature. And inside atoms, electron is not stationary, it is constantly moving. So hence, there is a wave associated with the electron. But there was a curiosity that, okay, if wave is associated, then where is the equation? Because every wave has an equation. So there is a curiosity, give us the wave equation. And that curiosity inspired Schrodinger to invent, to discover this wave equation. Now here we are using both invention also discovery also, because we can say that, okay, in this equation it's a combination of both. Using the natural principles, he is applying some jugaad, some technique, and he is coming up with a very interesting equation which satisfies our observation, and hence it is acceptable by the scientific community. Now let us derive this equation. So for the derivation, first we have to like consider some assumptions, some considerations. So some considerations we have to look into. So two important considerations we have to take into account before starting this derivation. The
Okay,
first
sir.
consideration is that the particle is not independent, it is not free, but it is bounded by some force. Particle is bounded by some force. And definitely this wave equation, Schrodinger, he basically created it for electrons. And we know that electrons are bounded by the positive force of the nucleus. So the electrons, the subatomic particles, they are always bounded by the force, nuclear force. So this assumption we have to take. And speed of the particle, speed of the particle is less than speed of light, isn't it? So this consideration we have to take, okay? Because the idea is that now when the particle speed it approaches the speed of light, then according to theory of relativity by Albert Einstein, some strange phenomena happens like time dilation, time slows down, and some more phenomena occurs, and we are not interested in going there. So we are assuming that okay, speed of the particle is less than the speed of the light. The particle whose wave equation we are measuring, because we know that okay, if a particle is moving with a velocity v, it is emitting a wave, and we are trying to find the equation of the wave, and that we are calling as Schrodinger wave equation. Now let us start with the derivation. Let's start. So what we are doing, that was done by the Schrodinger.
Yes, sir.
So we are already aware of wave function. So basically wave function, it is A, E, I, kx minus omega t. So this is a complex wave function. This is a, because here iota is involved. Iota, like iota is under root of -1, and it's an imaginary number. So this wave equation, we use it like it is the starting point. So this wave equation, we call it as complex wave equation.
Okay, sir.
And here capital A is the amplitude, E is the exponential function, and what is K?
The wave vector.
Wave vector. Very, K is the wave vector. X is the position. And X is a variable because we can plug any value of X here. And omega is the angular frequency. And small t is the time instant. So the idea is that this wave function, what is the significance of it? The significance of this wave function is very important. Basically, this wave function, it represents the position of particle. The position of particle in a space at time t. So the idea is there that in atomic structure, we already are aware of the concepts of orbitals, s orbital, p orbital, d orbital, f orbital. Now we know that, like, we know that, okay, hydrogen atom, it has only one electron, and that one electron is occupying the s orbital. We know that. Now the idea is that, so if I know the orbital, then I also know, the probability of finding the particle in that orbital. Okay. And so the idea is that at different time instances, like here, I can plug different values of t, and solving this equation, I will get different values of x. So this wave equation, using this wave equation, we can identify or get the position of the particle in the space at different time instances. Okay, at this particular time instant, where is the particle? At this particular time instant, where will be the particle? All that information we can get from this one equation. So this is a complex wave function. This function. So this is clear to us.
Yes, sir.
Just a minute. Now what we will do is, we will use this equation and do some mathematics around it. Like, so complex wave function, let me write it once again. So complex wave function is equal to A E I ax minus omega. So this is the complex wave function.
Yes, sir.
Now what we will be doing, we will be differentiating this complex wave function first with respect to the position, then with respect to the time, because this complex wave function has two independent variables, x and t. X is the position and t is the time. So let us do that. So if differentiating, differentiating this wave function with respect to x, first we will do this, then we will be also doing differentiating the same wave function, differentiating the same wave function with respect to time. So these two operations we have to do. And we are already aware that it is a function involving two variables. So we have to do partial derivative. So let
Okay,
us
sir.
do, yeah. So let us do that partial derivative. So we will be doing partial derivative of this wave function with respect to x. And okay, so when I am doing partial derivative of this wave function with respect to x, I will treat capital T as like a small t as constant. Only x will be treated as variable. And I know the differentiation of this function will be a e I ax minus omega t multiplied by differentiation of inner function. So ik. This is somewhat similar to this ik into psi. So this threshold, this is the psi, psi. We call it psi wave function. So this thing which we got, this is psi itself. So I can write ik psi. So this is very clear that okay, the wave function which we have, if we differentiate it with respect to x, I will get ik psi. Now
Yes, sir.
the same wave function, if I do differentiate it once again, if I differentiate it once again, that is a double derivative. If I differentiate it once again, then let us see what happens. Okay. So okay, let us differentiate this. So it will be ik, I can bring it here. A E I kx minus omega into differentiation of inner function, that will be once again ik, isn't it?
Yes, sir.
Now ik I can multiply, it will become I square k square A E I kx minus omega t. Now I know that I square is minus 1, isn't it? I square is minus, so it will become minus k square AEI kx minus omega. So I can write double derivative of the wave function with respect to position is this. Okay, this is clear to us. Now we are saying what we can do is this thing is our psi,
Yes, sir.
so it will become minus k square psi.
Okay, sir.
I can write it minus k square. So this is clear to us. Similarly, let us differentiate the wave function with respect to t, that is a time. Let us do that. So now we will be doing partial derivative of the wave function with respect to t, and we will get AEI kx minus omega t multiplied by, it will become minus I omega. Because when we are differentiating it, there is with respect to time, x will be constant, it will become 0 when we will be differentiating this, and it will be minus I omega. So this we will get. Okay. Now what we have to do? Okay, so now we can write it like this. Now this thing is the psi itself.
Yes, sir.
It will become minus I omega psi. Differentiation of this wave function with respect to. Now what I can do, I can multiply both the side with I. When I will do that, I will get the like differentiation of this wave function with respect to time into I is equal to, and I square I know -1. So minus minus plus 1 I will get omega sum. After all these calculations, we got two important result. Let me write it, like let us emphasize on that, because that is what we will be using in our derivation. So one result we got is this. One is this result which we got. This we have to use minus a square psi. And another very important result which we got, that is this. I now we will make use of this very soon. So until here it's clear. So we started our journey with this wave function. We differentiated this wave function with respect to x. Two times we have to differentiate, and we will get this minus k squared psi. And the same wave function we differentiated with respect to t, and we got this I t psi by dt is equal to omega psi. It's fun. Now we
Yes,
will use,
sir.
yeah. Now we will use one more concept. Like, see, it's a universal principle that total energy of the system is always conserved, either at the macroscopic level or microscopic level. It is like total energy is always conserved. It means that what I can say mathematically, I can say it like this: the total energy of the particle because here we are discussing this for the electron. So the total energy of the particle, if I represent it with capital E, if I represent it with capital E, it will be equal to kinetic energy plus potential energy. Why potential energy will be there? Because it is bounded by a force. We have already taken an assumption that the particle is not free. And whenever a particle is bounded by a force, it has some potential energy. So the particle which we are observing, it has a kinetic energy, it has a potential energy, and the sum of it is the total energy of the particle. Now what I can do, I can write it like this. Total energy of the particle is equal to kinetic energy, I know, half mv square, where v is the velocity of the particle. And we know that this velocity is less than the speed of light. And potential energy, we can represent it with capital U, because potential energy, we used to represent it with U. Okay.
Okay, sir.
Now, what I can do, I can write something like this. I am multiplying and dividing by n. So m square v square, that will become p. And m into v is p, so p square by 2m I can write. Let's see. I can show it here. I can show it here. See, p is equal to mv. So p square will be m square v square. What I did, I just multiplied by m and divided by n. So m square v square will be p square upon 2. That is what I did.
Okay, sir.
Now we have seen some like Based on de Broglie hypothesis, we have some result that we are using, and definitely I will prove it later on. But now, like you just assume it, that momentum of the particle, we can write it like h cross k. And what is this h bar?
The reduced Planck's constant,
It is the reduced Planck's constant, and k is the
the wave vector.
wave vector. So momentum, I can write it like, see, h we know, h is the Planck's constant, but this h, a bar over that, it's a reduced Planck's constant, and k is the wave vector. So instead of p, I can write this, and energy, it is reduced Planck's constant into omega. These equations are applicable for wave. What kind of wave? Wave associated with a moving particle. Because see, the idea is that na, a particle has mass. So definitely momentum, we will say m into v, energy is like half mv square plus u. But when the particle is moving, it is also emitting a wave. And that wave does not have any mass now. So how I will get the momentum of that? So this h bar k, like reduce Planck's constant into what is k?
Sir, the wave vector.
Wave vector. And angular frequency is associated with wave only now. So now what I will do, I will simply plug it in this. I will simply plug it in this. Let us plug it into this equation. So instead of E, I can write reduce Planck's constant into omega is equal to reduce Planck's constant into wave vector upon 2n. So the square is there. P square. Okay, this equation will. So this is like the total energy of the particle. So conservation of energy, like the total energy of the particle, the basic idea we used, and we now converted it into the form of the wave. So this equation is suitable for the wave associated with the particle. So if a particle is moving with a velocity v, this equation is applicable for them. Now what we will do, now we will apply some more jugaad, we can say that, in such a way that it follows the principles. Now what I will do, I will multiply both the sides. Multiply both the sides with wave function. With the wave function. And when I will do that, I will get something like this. Multiplied by wave function. It will be equal to reduce Planck's constant into k plus square upon 2n multiplied by once again the wave constant, like wave function. And once again, the potential energy. That is the total potential. Okay, so this is clear to us.
Yes, sir.
Now what we will do, we already had some result. Like this Just a minute, I will show you. So what I'm trying to do now is that this omega into psi. I am trying to replace it with this. Okay, because you see,
Okay.
omega psi is used here. I have already derived that. Okay, omega psi I can write like this: I into derivative of psi with respect to, and here uh, k squared psi. So here I have k squared psi. So k squared psi I can replace it with minus of double derivative of this. So this I will do.
Okay, sir.
So now it will become something like this. See, h bar will be as it is. So just yeah, h like this. Here I will write it with different colors so that we can emphasize on that. So this thing we got from the above equation. That is I, isn't it?
Yes, sir.
And here I can write reduce Planck's constants for whole square upon 2n and k squared psi. That what we can get minus this is what you will do, isn't it?
Yes, sir. So, but in the equation we have k square, but we are putting the value of minus k.
No, so here see k squared psi it will be minus of this.
Okay,
So
sir.
so that is what we are doing. That is right. So this is what, and this is the Schrodinger wave equation. Time dependent Schrodinger wave. So finally we have it.
Yes, sir.
Time dependent Schrodinger wave equation. I can write it here. Okay. So just let me write it once again. It will be equal to minus x square by 2 and double derivative sum plus potential energy psi. Okay, nice. So this is the wave equation. Now here some more discussion we can do, like the terms which we got, like this
Yes,
one.
sir.
Just a minute. So here one term I got is this. So what is the significance of this term? This term basically it gives us an idea that how wave function changes over time. Because this is the equation and this term, because this term is having time term, because change with respect to time. So how wave function changes with time? How wave function changes with time? How wave function changes over time. It unfolds the future of the wave. It unfolds the future of the wave. Similarly, the next term, one more very important term, that is the this one. This term gives an idea about the position, curvature of the function, the trajectory, curvature of the function. Here, it is the wave. So curvature of the wave, we can get an idea from this term. And the potential energy term, which we had, it tells us about nature of the field, whether the field is conservative, non-conservative, all that. Nature of the in which particle is subjective. This is the idea. Okay.
Yes, sir.
And one more analysis we can do here. Like whatever wave equation we have, let me write it this way. So this is the Schrodinger wave equation. Let the box be there. Now what I will do, I will compare it with my energy equation and I will get something very interesting. Compare with, we remember that the energy equation we had, we multiplied both the side with psi.
Yes, sir.
So this was the energy equation. We multiply both the term with psi. Actually, we multiplied it. And now we can compare it and we can get something very interesting observation we can make. So when we compare it, we can say that E cap is equal to I H bar this. Similarly, I can say that kinetic energy cap is equal to minus H bar square del square upon 2m upon del x, something like this. And I can also say that potential energy cap is equal to U itself, capital U. And one last equation we will discuss for today's session, that is time dependent Schrodinger wave equation in 3D. So no derivation, this just we will tweak it a bit, then we are done. So let us write that.
Okay, sir.
Time dependent Schrodinger wave equation. Okay. So the same equation now see 3D means here we are taking position only along the x-axis. Then it will be along the x-axis, y-axis, and z-axis. So for that one concept of mathematics we have to use that I will tell you first that concept, then we will uh, get the equation.
Okay, sir.
Concept of this Laplacian operator. Laplacian operator. It is the reverse triangle. So this Laplacian operator, it is equal to del by del x square plus del by del y square plus del by del z. So it will take care of this. So now we just have to do one thing in this equation, then we will get the equation in the 3D form. psi is equal to minus h square by 2n square by then x square. Okay, sorry, no x square and all. Simply we will do the Laplacian operator, and it is square. Okay, sorry, Laplacian operator is square. Let me reverse triangle square. So here I will write reverse triangle square psi. That's it. And we have the Schrodinger wave equation in 3D. Time dependent Schrodinger wave equation in 3D. We have it. Okay.
Okay, sir.
Okay.